doing today? What are we doing? Y'all able to see that? So we're good? Okay. Filtration. We're going to talk about filtration. Okay? Talk a little bit about filtration. All right. But just as a quick little overview, we talked about the X-ray tube last semester, right? This past summer. So just as a little overview, are you able to see the mouse, the arrow?
Mm-hmm.
Okay, good deal. So at this end of the X-ray tube, what two components do we have here?
No, the rotor and the stator.
Filament and focusing cup.
Right, filament and the focusing cup. And remember, the focusing cup was made of nickel. And the filament, the primary element, is tungsten. But do you remember what is mixed in with the tungsten?
Thorium.
Thorium. Yeah, exactly. Thorium. Thorium helps to minimize vaporization, because that's when the filament heats up. The tungsten gets released in a gaseous state, and then the metal deposits itself on the inside of the glass envelope. And I don't know if you remember when we looked at the X-ray tubes in lab, some of the X-ray tubes kind of had a brownish tint inside, and that's from where the tungsten metal had deposited itself inside of that glass envelope. So the thorium, it helps to reduce some of that vaporization, but it's still going to happen. And the downside of that vaporization is during an X-ray exposure, electrons that come off that filament will be drawn to that metal inside of the glass housing instead of making it to the anode. And so we lose out on X-ray production. It reduces the efficiency of X-ray productions. So as a tube ages, that's just something that will naturally occur. So we've got that filament and we've got focusing cup. And then those electrons will hit the anode. But do y'all remember the specific spot on the anode that it will hit? What is that area called?
The actual focal spot.
Exactly. Good. Yeah, the actual focal spot. Right, the actual focal spot. And then the area from which those X-rays will diverge out, because the electrons hit the actual focal spot, and then they diverge out from what do we call that area from which they diverge off the face of that anode?
Effective focal spot.
Yeah, great. Effective focal spot. Exactly. Effective focal spot. And remember, the X-ray tube, the anode is angled. The anode is angled so that the actual focal spot is a bigger area than the effective focal spot. We want that actual focal spot to be larger so that it can better dissipate the heat. And we want the effective focal spot to be smaller so that we have better image sharpness. Okay? Yeah, good. And then the structure that surrounds the anode and the cathode, that's that glass envelope. It can be made of metal. Ours typically are made of glass. So it's that glass envelope, and that maintains the vacuum so that the electrons will be able to make it from the cathode over to the anode. And then the anode is connected by an anode stem. And do you remember what that anode stem is made of? Begins with an M.
Molybdenum.
Yeah, molybdenum. Exactly, molybdenum. And the face of the anode, where'd my mouse go? The face of the anode is primarily composed of tungsten. And what is mixed into the tungsten on the face of the anode? Begins with an R.
Rhenium.
Yeah, rhenium. Yep, exactly. That helps as the anode heats up and expands and contracts. That helps to reduce the brittleness of the anode. Okay. And then the backing of the anode is made of the same material that the stem is made of. It's made of molybdenum. So it's a thick layer of molybdenum. But molybdenum is used as the backing because it does have a high thermal capacity, and it's lighter weight than tungsten. I don't know if you remember how heavy those anodes were, but they do have some weight to them. They'd be even heavier if they were fully composed of tungsten. And then that anode is connected to what? What is this? It's made out of copper, has bearings inside.
Rotor.
Yeah, it's the rotor. It's the rotor. And then what is the only component on the outside of the glass envelope?
Stator.
Yeah, this is stator. And remember, the stator is an electromagnet because it's coils of wire and there are magnets in it. And then the rotor is also an electromagnet because it is a copper cylinder and it has an iron core. And if you remember, the rotor turns not because of a direct electrical current, but current is produced inside of the rotor via the stators. So when current gets sent to the stators, it produces this fluctuating magnetic field, and that fluctuating magnetic field will cause current to flow in the rotor, and a magnetic field is also produced in the rotor, and that causes that rotor to turn because it will interact with that iron core and it causes that rotor to spin. So does that ring a bell? A little bit? Okay. And then when the x-rays are produced, there's a thinned area of glass. So the glass is made a little thinner so that it will allow a majority of the x-rays to make it out of the tube. Okay. And then they come down through the collimator and to the patient. So, we talked about the x-ray tube last semester. We also talked about x-ray production. So what we're going to start with today is something called filtration. And that thinned area of glass actually serves as a filter. Even the oil that is inside that the tube is immersed in, that serves as a filter. And then you'll notice too, there's a little structure drawn in here. This is a filter as well. So we're going to talk about filtration and the purpose that it serves. Okay. So you okay up to this point? Oh, a couple more questions. With x-ray production, there are two ways that x-rays will be produced. Do you remember what they are? One begins with a B.
Brims and characteristics.
Yeah, brims and characteristic. And remember, we always get brims, but characteristic we only get when what happens or what is true.
When it's at 70 keV or higher.
I'm sorry, what'd you say, Sierra?
When it's at 70 keV or higher.
Exactly. So on your control panel, as long as you're at 70 kVp or higher, we also get characteristic x-rays. Yep, exactly. Okay, good. All right, so filtration. So what we're going to look at are different types of filtration. We're going to look at recommendations regarding filtration, and then we're going to look at regulations regarding filtration. So the types, recommendations, and regulations. So the function, another name for function is purpose. Okay, so what do you think the purpose of filtration is? What do you think the purpose of tube filtration is? What do you think that means? We're filtering the beam.
We're just taking out the low energy photons that aren't very helpful to either the patient or the image.
Okay, so, and you kind of mentioned the function as well as the mechanism here, which is how it does it. Exactly. So in terms of the definition, the function or the purpose is to reduce patient exposure, specifically entrance skin exposure, because like Casey said, they're not valuable. These photons aren't valuable. So the purpose or the function is to reduce entrance skin exposure. We want to minimize the amount of exposure that the patient's skin gets. It's pointless if the skin absorbs those x-rays. Okay? So the mechanism means how does it do it? That's what's meant by mechanism. So how does filtration minimize entrant skin exposure? Like Casey said, it absorbs the low energy photons. So filtration absorbs low energy photons. That's what it does. And we have two types of filtration that we'll run through. We have inherent filtration, and then we have added filtration. And when it comes to inherent and added filtration, there are standards that are in place. The NCRP, does anybody happen to remember who the NCRP is? Anybody happen to remember?
Just guessing, like National Committee on Radiation Protection.
Very good. You got 3 out of 4. It's the National Council on Radiation Protection. Yeah, exactly. National Council on Radiation Protection. Yep. So they make recommendations regarding various aspects of the X-ray equipment. So we'll look at those recommendations pertaining to inherent and added filtration. But then there are also regulations that govern filtration. And do you remember the CFR, what that stands for?
It was like something federal regulations.
Yeah.
First word.
It's Code of Federal Regulations. Great. Yeah, Code of Federal Regulations. Exactly. So these are government mandates from the federal government. Okay, good. So everybody's all right so far? No one's lost on slide 3. We're off to a good start. Okay. All right, so filtration types. We'll start with inherent. So what do you think inherent filtration means? What do you think inherent filtration means? If it's inherent.
It's already built in the tube.
It's already there. Yeah, it's already there. And actually the purpose of these things that are already in the tube, the main purpose isn't actually to serve as a filter, but these components have some other main function, but just the fact that they are there in the tube, they do end up serving as a filter. So yes, inherent means those components, those materials are already present in the X-ray tube. And their main purpose happens to be for something else, but they also end up serving as a filter. And so here are the components that are considered to be inherent filtration. Okay, the tube window. Well, really, the purpose of the tube window is for what? We talked about that thinned area of glass. What is the purpose of the tube window?
So that it's easier for the X-ray to shoot out. Is that right?
Yeah, that tube window has to be there to allow X-rays to come out. What if that tube window, what if the bottom part of that glass envelope was made of lead? We wouldn't get any X-rays coming out. So the purpose of the tube window is to allow the X-rays to come out. But since it happens to be in the primary beam, it is going to filter a certain number of those X-rays. Okay, the oil that the tube is immersed in. What did we say the purpose of the oil is? What does it do?
Dissipates heat and protects against electrical shock.
Yeah, exactly. It helps to dissipate heat, to get heat away from the tube. Because we've got several thousand degrees that ends up being built up in that tube, just from one exposure. So that oil helps to get rid of it. And also, too, because of the high voltage that is flowing through that tube, it does help protect from electrical shock. So that's, the purpose of the oil. But since the oil is there and the X-rays have to travel through it, that oil is going to absorb a certain number of X-ray photons. The tube port cover, this is referring to well, let me point out, this is referring to this little structure here. In other words, there has to be a window. It's called a tube port window. So the protective housing has to have a window. And I don't know if you all remember seeing that in lab when we looked at the parts and I had the protective housing, the full unit together, and I had it turned upside down so that you could see, oh, here's where the collimator would attach. But there was also a little, it was kind of like a little insert in a window. That's the tube port cover. Why does that protective housing need to have a tube port or tube window? Why does the protective housing have to have a window? Same reason the glass envelope has to have a tube window. We need those x-rays. If they make it out of the x-ray tube, we also want those x-rays to make it out of the protective housing. Okay. And then another filtration device that's inherent is the collimator mirror. I know we haven't talked about collimation yet. We'll talk about it. But inside of the collimator, there's a mirror, and you'll see that in a moment. Okay. So far, so good? All right. So here's your tube window. It's a thinned area of glass. Here's your oil in here. This is the tube port cover, this segment here. And then here's your collimator mirror. So all four of these things are classified as inherent filtration because they are inherent. They are part of the X-ray tube assembly and part of the collimator. And the main purpose isn't to serve as a filter, but since they're there and the primary beam has to go through there, they do end up serving to filter out the low energy X-rays so that patient exposure can be minimized. Okay. By the way, do you know why this mirror is here? It's a mirror. So right in the middle of the collimator, there's a mirror.
Is that to reflect the light source of the collimator?
Yeah, exactly. Exactly. And we'll talk about beam restriction on Wednesday. But, when you press that light on the collimator, the light shines, hits the mirror, and then it gets reflected down this direction. Why do we have to have the mirror? Why can't we have this light bulb right here in the middle of the path?
It would get in the way of the x-rays coming down.
Okay, and what do you think would happen? What do you think you would end up seeing on your image?
Every image would have a light bulb in the middle.
Every image would have a light bulb. It would look like the patient swallowed a light bulb. Exactly. So it has to be off to the side. Okay. So that's your inherent filtration. You may be asked on a quiz or a test to identify or list the inherent filtration and to provide a definition. So you're comfortable with being able to list those things, those 4 items? Okay, pretty straightforward. It's really just memorizing what they are. Nothing difficult about just memorizing them. Added filtration. What do you think added filtration is? What do you think a definition would be for added filtration?
The materials that we add to the filtration.
It is something that's added. Yeah, and it's added on purpose. It's added to meet regulatory requirements. Exactly. So it is added to meet regulatory requirements. Because I already mentioned to you, we'll look at recommendations and we'll look at regulations. So added filtration is intentionally added to the tube or somewhere in that path. It's intentionally added into the primary beam to meet regulatory requirements. Okay, to meet the requirements. And there are different types of added filtration. The most common one is aluminum, and that's what our X-ray tubes have. Our X-ray tubes have an added sheet of aluminum. There's another type of added filtration, and it's referred to as a compound filter. Another name for it is stack or composite, and we'll take a brief look at this filter, compound filter. But the most common is aluminum. Okay. So where's that added filtration? It's right here right in the middle of the primary beam here. So the added filtration is just it's a sheet of aluminum that is inserted in between the protective housing and the collimator. So it's not something that you can see. When you look at the X-ray tube, you're not going to be able to see this sheet of aluminum, okay? Because it's sandwiched in between the collimator and the X-ray tube. But it is placed there to meet regulatory requirements because the system has to provide a certain level of filtration to ensure that we are minimizing patient exposure. So like I said, the most common is aluminum, and we're talking about thin, we're talking about millimeters worth of thickness. So this is something that's a very thin sheet of aluminum. I know here it looks thick, but it's not very thick. We're talking about millimeters of thickness. Okay. So like I said, most of the time it's aluminum. That's what it is in our X-ray equipment. There are some units though that may use compound filters. Okay. It's possible that some diagnostic X-ray units may use compound filters. Most of them, though, tend to use just straight up aluminum. But the reason it's called a compound filter or a stack filter or a composite is because if you notice here, it consists of more than one metal. That's why it's called composite or stack. And it's called stack because they're stacked on top of one another. So it is possible to have a multi-metal filter, and typically the multi-metal filters are composed of copper and aluminum. Copper and aluminum. Why not just the aluminum? You can. I mean, you can, and like I said, most of ours are, but there are some vendors, some manufacturers that choose to also use copper. Copper simply reduces the thickness of the added filtration. So instead of having a particular thickness of aluminum, you can actually use a little less aluminum because you're using copper. Copper is very efficient at removing low energy photons. So it just makes the added filtration a little bit thinner than if you were to simply use aluminum by itself. The reason it's not as popular as just flat out using aluminum is because copper is expensive. Copper is expensive. Okay. But like I said, there are some units that the vendors may decide we want to use copper and aluminum. If they use a compound filter, then the metal that has the highest atomic number needs to be placed closest to the X-ray tube, like you see here. Copper has an atomic number of 29. Aluminum has an atomic number of 13. So copper would be placed closest to the X-ray tube, and then aluminum would be right underneath the copper. Okay. So basically, what's the advantage of using copper and aluminum? What would you say if you were asked about it?
It's less thick.
Yep, it just makes it less thick. It's just less thick. The disadvantage, though, is copper's more expensive. Copper's more expensive. Okay, but still something that you need to be familiar with. Do you think you'll necessarily know what the added filtration is in the X-ray units that you're working with? Not necessarily, unless you pull out the specification manual for that unit. But that's okay. It's safe to pretty much assume that it's aluminum, that it's simply a sheet of aluminum. Okay? So you okay with that? Okay. So added filtration and inherent filtration. When you add them together, we get something that is referred to as total filtration. So total filtration is the inherent filtration, which is the tube window, the tube port, the oil, and the mirror. So it's those four things plus the added filtration, which is this sheet of aluminum. That's what yields total filtration. Now, as far as the amount of filtration, that units should have. The standard material that is used to judge the amount of filtration is aluminum. Okay, that's the standard material that is used to judge the thickness of the materials that should be used. And this will make sense when we kind of go through this. I want to point out some terminology to you though. Aluminum is measured in millimeters. Okay, so millimeters of aluminum. If you ever see in a textbook something written or in a paper, wherever, millimeters of ALEQ, this stands for millimeters of aluminum equivalents. Okay, and I'll talk a little bit more about this when we get to the point here in a slide or two. But for right now, know that the standard material against which to judge filtration is aluminum, and it's millimeters of aluminum. Okay, and you'll understand this a little bit better momentarily. So we're going to look at recommendations, which is from the NCRP, and we're going to look at regulations, which is the CFR. And just so you know, it happens to come from something that's called report number 102. You don't need to know that it's report 102, but what's important to note about the National Council on Radiation Protection, they have numerous publications, and so all of their publications are identified by report number. So when it comes to recommendations regarding X-ray equipment, it comes from report number 102. We'll be seeing this again because there are other recommendations concerning X-ray equipment, not just filtration. With the regulations, it happens to come from something that's called Title 21 CFR, Part 1020.30. I did post a link for you with the Code of Federal Regulations, which will bring you to this document so that you can see not only the regulations for filtration, but other aspects of the equipment as well. And we'll be talking about those too at some point throughout the semester, just like we will be talking about recommendations. We're going to be talking about regulations too, not just relative to filtration, but other things. So how about before we get into this, why don't you go ahead and take a break. We'll come back at you want a 15-minute break?
Yep.
Okay. So how about you come back at 9 o'clock and we'll go through the rest of filtration. So you good?